Can a demon defeat the second law of thermodynamics? This is actually a very serious scientific question. To understand this, you're finally going to have to meet Maxwell's demon. As well as unifying the equations of electromagnetism, James Clerk Maxwell was one of the founders of statistical mechanics. Understanding that entropy was a statistical phenomenon, he came up with a thought experiment to explore just how fundamental the second law of thermodynamics really was. He imagined a box with two halves, sealed by a wall between them. The wall has a tiny door, large enough for a single molecule to pass through. The air throughout the box is the same temperature, so even if we open the door, temperature would stay the same. The halves are in thermal equilibrium with each other, and if the box is isolated from its surroundings, then this is the state of maximum entropy. Let's introduce the demon. The demon has the ability to observe the speed and trajectories of individual particles in the system. It can also open and close the door between the sides. Every time the demon sees a high-speed particle approaching from the right, it opens the door to let it pass to the left side. And it lets low-speed particles pass left to right. Soon enough, the left side is full of fast particles and is hot, while the right contains slow particles and is cold. We are no longer in thermal equilibrium, and the entropy is lower than before the demon started. This temperature differential can then be used to drive a heat engine and do work. But all of this appears to have been done without exchanging energy or entropy with the outside universe. This seems to violate the second law of thermodynamics, which demands entropy remain constant or increase unless energy is exchanged with the outside universe. Believe it or not, Maxwell's demon was seen as a serious problem for the second law for many years. Physicists tried to figure out a flaw in the argument. It turns out that there are plausible, non-demonic, or even intelligent mechanisms to detect approaching particles and open the door, mechanisms which, in principle, don't increase entropy. But it turns out there's one last step in the process of sorting particles where the increase of entropy is unavoidable. Weirdly, it's not in the measurement of particle trajectories or the motion of the door. It's in the storage of information. It's in the memory of the demon. See, in order for the demon to do its job, it must learn about the particles. The demon, or the particle sorting system it represents, must start in some known predictable state, which is altered by interaction with a particle into some unknown state. From our point of view, the randomness of the particles decreases, but that randomness is transferred to the memory of the demon. But even demons have finite memory. At some point, the system for sorting particles needs to be reset to continue its work. To erase the information of past sorting means to transform some arbitrarily jumbled state into a single known state. That's a physical process that reduces the demon's internal entropy, and that takes an irreversible transfer of energy. The demon has to radiate heat, which means transferring entropy back into the box or to the universe. Either way, the second law is preserved. This resolution was proposed by Rolf Lindauer in 1960, nearly 100 years after Maxwell proposed the conundrum. Lindauer's principle states that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase. And this has come to be seen as a fundamental limit to the efficiency of computation. Both Maxwell's conundrum and Lindauer's resolution are fascinating because they highlight the fundamental link between entropy and information. Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. He defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system, the latter applies specifically to thermodynamic systems. And there's a third, perhaps even more fundamental type of entropy. That's quantum entropy, also known as von Neumann entropy. It describes the hidden information in quantum systems, but more accurately, it's a measure of the entanglement within quantum systems. In fact, the evolution of quantum entanglement may be the ultimate source of entropy, the second law, the limits of information processing, and even the arrow of time.